Alright, my math students, gather here. Yes, today we are taking a lesson in abstract algebra where we are going to solve or unpack this tedious question that has been the headache for students for some number of years now. We are going to prove this question, unpack it to the very smallest possible way such that you can understand it and solve it yourself. Okay, so let's dive in. If you have not hit the subscription button, do that. Hit the like button, share with your friends out there. Reality Math got you covered. Let's dive into it. Okay, let G be a group and let X be a G set. Define a relation R on X by X relates with Y if and only if there exists G in G such that Y equals Gx. Prove that R is an equivalence relation. So we are going to prove an equivalence relation here. So let's see. First, let's identify key things down. First, we let our G be a certain group. From there, we are going to show that what our R is an equivalence relation, but we have to also see that how does X relates with X relates with Y is saying that if and only if or there exists what? This is if and only if or there exists some G in G such that Y equals Gx. So we are going to use this to prove our equivalence relation. But first we have to identify that for equivalence relation, there are three axioms that this must fulfill. This relation must fulfill. If these three are fulfilled, then we see that it is an equivalence relation. First, you must show that what? It is reflexive. It is reflexive. If it is reflexive, this means that our A or X relates to X, or X mounts back to itself. But the second one, it must be symmetric. Now, if it is symmetric, it means that what? If X, or we suppose that X relates to Y, then our Y must also relate to X. If X relates with Y, then Y must also relate to what? X. So here is X. So our Y relates to X. Then third, transitive. If X relates to Y and Y relates to, or Y relates to some Z, then our X here, our X relates to Z. Then if it is done, then this is our transitive. This is transitivity. Okay. Then we can see that our relation is an equivalence relation. So first, let's get in. Let's start with what are reflexive. So for it to be reflexive, we first have to pick, let's first pick what X. So by definition of the relation, we are saying that there exists some G in G such that Y is equal to what Gx. But our G is a group. By definition of G, G contains what? E is in what? G. So let's consider this E in G. So consider our E in G. So if you consider the identity element in G, what does that mean? So E composed with X. Here our X is from what? G set. So E composed with X is going to give us what? Our X. So here we can see that there exists some what? There exists some G in G, which is our E here, such that our Y is equal to what? Gx. So there exists what? Our G, which is what? E in G, such that what? Our Y is equal to what? Our Y is equal to Gx. Or which is or what? We can see that E dot X is equal to our X. Our E dot X here is equal to X. Then let's proceed. Okay. Then we see that hence it is what? Hence R is what? Is reflexive. Is reflexive. If our R is reflexive, we are now going to look at symmetric. Let's suppose that x relates to y. So suppose our x relates to y. What does that mean? If x relates to y, it means that then we are going to have that what y is equal to gx. Then we are trying to prove that what y should relate back to x. And how can that be? Let's consider some g inverse in what? In our g. If we consider g inverse in our g, then we have g inverse multiplying our y is equal to our g inverse multiplying out our gx. Alright? Then we are going to have over here g inverse y is equal to what? G inverse g of x. But g inverse g is e. So we are saying that g inverse y here is equal to e dot x, which is equal to x. So what is this looking? This is looking at what? G inverse y is equal to what? Our x. And this means that what? Our y relates to x. Our y relates to x. So if our y relates to x, this shows that hence our y relates to x. Notice that if x relates to y, how it looks like. If x relates to y, we are saying that y is equal to gx. What about the other way around? If the other way around, that means that our x here is going to be equal to, here this y, so must be x is equal to something times our y. So this is going to show that hence our y relates to x, and we can say thus we can see that what there is this g inverse in g such that there is this g inverse in g such that what we can clearly see over here that g inverse in g such that our y has related to x, which is g inverse y such that what our y relates to x. Okay, then we can see that what the relation is our relation is symmetric. Then we are now looking at what it being transitive. So suppose that then we look at suppose x relates to y, then if x relates to y, we can see that y is equal to gx. And also we are also supposing that our y relates to z. If y relates to z, it means that z is equal to what? Gy. Okay. Then we are trying to prove that our x also relates to what? Our x relates to z. How do we do that? Here we can see that y is equal to gx. So let's try to substitute that over here. If y is equal to gx, then let's substitute that. Since y is equal to gx, we can put that in. We can see that z is equal to g into bracket gx. So this is going to be z is equal to gg of x. Where we say that, okay, so our gg is in what? Is in the main group g. Then we can see that, okay, truly our z is equal to what? Our z is equal to, we can let our gg be equal to some k, where our k is what? In our g. We can also equally leave it this way, but just to make it more simpler, so this is what? Our kx. And what does that mean? This means that our x relates to what? Our z. Our x relates to z. Hence, we can see that, hence, the relation is what? Transitive. You can pause your video one by one to understand the procedures, or pass a comment or your question in the comment box whilst we address that adequately. So since the relation has fulfilled these three axioms, we can see that for this we can see that our relation is what? First, reflexive. So we conclude that, okay, since R is what? Reflexive. Since R is reflexive, and the same time our R is what? Symmetric, and what? Transitive. Then our what? Our R is what? The relation. Then the relation is an equivalence one. It's an equivalence relation. Stay tuned as we solve more of these questions.